Hello and welcome. In this video, we're going to discuss voltage to ground. Voltage to ground is a little bit different than voltage drops, but they include each other. So we know that KVL, Kirchhoff's voltage law, states that we will have a voltage drop across each one of our resistors, and all of those voltage drops will add together to equal 27 volts. That's what it says over here. It says our source voltage is the sum of the voltage drops that we have in the circuit, however many series components that we have. We can also say that the source voltage can be subtracted from each of those voltage drops, and we should be left with 0 volts at the end, right? Both those state the same thing. That just tells us that the ground location is our 0 volt location. So to get our voltage to ground at each point, we need to identify where our point is. In this first point here, point A, we can say that node A starts at the top here, and we see from our voltage source, our positive terminal, we go straight into point A. There's no resistance between our top of our voltage source and point A, which means that the voltage at point A is equal to 27 volts, right? It's our total source voltage. To get to point B, though, we lose something. We have to travel through R1, and we know R1 consumes a voltage, VR1. Right? So we know that we have a VA node, 27 volts here, and we're going to drop a voltage across R1. We got to calculate that out, and then we'll be left with whatever is at node B, and so we'll subtract them. So first goal is going to be VR1. We have the equation here, our voltage divider equation. It says that we want VR1, the voltage across R1, so we place R1 as our want resistance on top of our equation, and then on bottom we have our total resistance. So we need to figure out what our total resistance is for this circuit. So let's do that first. Our total resistance is equal to the sum of all of our resistors. We look at the resistors there, and we see each one of them are kilo ohm values, so we'll just add them up. 3.5 plus 2.4 plus 6.4 plus 1.2, and that gives us 13.5 kilo ohms. So our RT for this circuit is equal to 13.5 K ohms. We can use that to determine our voltage drop. We'll plug that straight in. We'll say that that goes in on the bottom. So we'll say that our VR1 is equal to our R1 value, 3.5 K ohms, divided by 13.5 K ohms. These two Ks are going to cancel each other out, so we can leave them off of this calculation. And then we can multiply by our V1, which is the 27 volts. And that's going to give us the voltage drop that R1 consumed. So we'll say that we have 3.5 divided by 13.5. And that is multiplied by our 27 volts. We're left with 7. So we expect VR1 to equal 7 volts. So it'll consume 7 volts. Minus 7 volts, right? That's what it's going to leave behind. And so that means that when we look back at our voltage drops, we see 27 starts at the top here. We lost 7 across our R1, so we will be left with the remainder of that. So let's calculate that out. We'll say that we had 27 before, we lost 7, and now we're left with 20. So node B should be 20 volts. So move on through here, we can calculate the voltage drop across R2 the same way. We can say that there's going to be a VR2 drop across R2, and that is going to allow us to calculate out node C. So we'll start with that. And we can even use the same voltage divider equation. We can say that VR2 is going to be very similar, but we're going to put R2 on top. 2.4 K goes on top. 13 K is still our total resistance, 13.5 K. And we'll multiply that by our 27 volts. And that's going to give us our voltage drop across the next one. So we can reuse the equation we had right here. Instead of 3.5 on top, we want to place 2.4. So now we know 4.8 volts drops across R2. So instead of VR2 here, we'll say that we lost 4.8 volts. Now we know what point C is. Point C is 4.8 volts less, so minus what we have right now. We are at 20 before, so we'll say minus 4.8. We're at 15.2 now, so point C is 15.2 volts. We can keep going with this. We can replace our top up here of our voltage divider with our R3 value, 6.4. That gives us 12.8. So now we've got 12.8 volt drop. We need to know, keep in mind that this should be less than the remaining voltage, right? 12.8 volts is less than 15.2 volts. So we can subtract that out. We can say minus 12.8 And that's going to be what we have at node D. Node D has 2.4 volts. We can figure out the voltage drop across R4. We know that it should equal 0 on the other side, so we actually expect 2.4 to be the voltage drop across this R4, but we can calculate it out. We can plug that R4 value on top, 1.2, and we're left with 2.4, and that confirms that we got the correct value there. R4's voltage drop is 2.4, which means that we're left with 0 volts at the end, and that's what we wanted. Okay, let us know if you have any questions.